Hello students, in this session we will see the chapter of laws of motion, right? So the topics that we will discuss in this chapter are like Newton's three laws. We will see all those three laws, right? You might have learned this one in your lower grades. As if now, we will see those laws statement will also be done. Same way, we will see how to use mathematical relation using those statements. Those things will also be seen in this chapter, fine? Then we will see like friction and the types of friction into it, fine? So in the first session, which means in this session we will see all those three laws. Same way we will do the first beginning part of the friction, okay? So in the next session we will do all the stuff that are related to friction and the fictitious force, right? So we'll see extra component which is like fictitious force. We will do those things in the next session. In the third session we will do motion of car on a circular track, and then we will do like motion of car on a banked road, fine? So we'll do some extra concepts like contact forces and all those things in the third session, right? So we need around like 3 sessions to complete this chapter, right? So let's jump into this chapter. The first thing is Newton's first law, right? You might have already learned in your lower grades, fine? There are not any mathematical equations that we could actually use from the Newton's first law. It is just a statement, right? Based on the logic and intuition, right? So what this statement actually means is if you're going to put an object in a space, it is simply at rest, right? After some time, you just take some time and then go and look at the object will be at rest, okay? So when an object is at rest, it will be at rest irrespective of the time that you're going to take, okay? So even if you look at it after like million years, it will be at rest, okay, in the external space. That's what that represents. Same way, if the object is at constant motion, which means when it is at a constant velocity, okay, at particular direction it is oriented and then it is also moving with certain constant velocity. Even in that situation, the object will be having the same velocity. It might have different position, but the thing is it will have the same velocity. Even if you look after some time that particular object, even if you just inspect that particular object after some long time, still you will have the same velocity for that particular object, okay? So that is what the Newton first law actually means. This is purely based on the intuition and based on all those philosophers who worked on looking at the planets, okay? And same way, so based on this logic we'll be able to build all other concepts. So the first thing is simple, and it is based on simple intuition, which is the object tends to be in rest or at uniform motion. So it will be at rest or at uniform motion, which means at constant velocity. You shouldn't have any acceleration into it unless it is acted upon by an external cause. So unless you push it from the outside or pull it from the outside, in that situation you will have the change in velocity, or else it will have the same velocity. That's what this first law represents, okay? So this is just the statement. We wouldn't make any mathematical, we wouldn't be able to get any mathematical equation from this first statement, but from the second and third statements, second and third law, we will be able to derive what is meant by force. So from the second law, we will be able to get this, what is the external cause. That is something that we will be able to determine. Same way, in the third law, we obviously know every action has an equal and opposite reaction, so we'll put in like negative sign. So from second and third law, we will be able to derive mathematical equations from those two laws, okay? So you should be clear with the first law. This is just a simple one. Let's see what the second law is. So second law is force is directly proportional to. So force is nothing but the external cause, right? So when you are going to give external cause from the outside, we'll call it as force, right? Okay, so how should I actually measure the force? That's what the second law represents. Let's see what it is. Force is directly proportional to the rate of change. Okay, so what does it actually depend? So it depends on the rate of change in momentum. So this is the new term that I'm going to introduce for the second law, okay? So rate of change, what actually means rate of change? How does it change with respect to the time? Okay, that is what is meant by rate of change, right? We might have learned this one in the previous chapters itself. So when you get like rate of change, you should put that parameter in the numerator and divide it with the time, okay? So in the situation, if the interval was so small, then I'll be able to use the differentiation. Therefore rate of change actually means d divided by dt, right? So I'll be able to put d divided by dt. So what should be the parameter in the numerator? That's what I need to know. So the parameter that I'm going to put in the numerator is actually the momentum, okay? So this is the new term that I'm introducing here. So based on all the experiments, so this was the final verdict that I got, which is force is directly proportional to that. So I'm just going to give an external cause. So based on that external cause, you're going to have some changes with respect to the body. Okay, so those two changes will reflect on the mass of that object. Same way it will reflect on the velocity of the object. Okay, so it actually reflects on the mass and then the velocity. So momentum is actually the multiplication of mass and then the velocity. Okay, so you do not have any fundamental proof. Why did we multiply mass times velocity? The reason we did multiply those two things were because it depends on the change in velocity, right? Whenever you have an external cause, you are going to have velocity change, so that should be considered. Same way, if the mass was huge, then the change in velocity will be less, then the impact will be less, as the mass is huge, right? So the velocity will be like less. So these two parameters will come into picture. Okay, therefore rate of change in momentum, therefore momentum is nothing but the mass times velocity. Fine. So this is something like a taken that I've taken it out of the blue. Therefore in change in momentum actually means p. So that's the symbol that I'm going to give it to the momentum. So p is a vector quantity, therefore vector p is equal to mass doesn't have any direction into it, so that doesn't make sense. So momentum depends on the direction of the velocity, which is like p m v vector. Okay, so this is the second law. So second law actually means force is directly proportional to the rate of change in momentum. So we will see the application for this statement. As if now what you need to know is, whenever a force is applied, what will happen to it is the velocity of that particular object will change. Okay, so how far does it change? That will give me the force that is acting on that particular object. Okay, right? So force is directly proportional to the rate of change of momentum. So from this differential equation, let's find out the equation. Okay, so I wouldn't be able to use every situation, like change in momentum, rate of change of momentum gives me the force. Okay, so let's differentiate it and let's find out the final result. Okay, so that's simple two-step process. So here vector f is proportional to, so that's what I have given in the statement, right? So I'm just going to frame an equation for the statement that I've told you. Therefore vector f will be proportional to d vector p divided by dt. That's how it should be, right? Now let's do the differentiation. So let me plug in mv instead of p, and then if I do the differentiation, let's see what I end up getting. So here if I do the differentiation one more, so if I just put an mv, you will have like d m vector v divided by dt. That's what you'll get, right? In this situation, let's consider the mass to be constant. Okay, so in majority of the Newtonian mechanics, mass will be considered constant because the mass of the object is not going to change, right? So only in relativistic theory where you will have the mass to be changing. Okay, so that too, when you study materials in a microscopic level, in that instant mass is actually a relative parameter in majority of the Newtonian mechanics. Okay, which means in the real time situation mass is going to be constant, therefore I'll just factor out the mass. So you will have, so this is like Newtonian mechanics, right? Obviously, so I'll just factor out the mass. You will end up having m d vector v divided by dt. Okay, so the only parameter that needs to be differentiated over here is the velocity, right? So this is something that we have already learnt in motion in a straight line. Okay, so when you differentiate velocity with respect to time, you end up getting the acceleration. Fine. So the differentiation of the momentum in the Newtonian mechanics gives me mass times the acceleration. Okay, therefore vector f is proportional to, fine, so vector f is proportional to mass times the acceleration. Okay, so now I'll have to remove this proportionality thing. So if I have to remove the proportionality, then obviously I'll have to multiply a constant to it, right? So you do an experiment and then you get the constant. Generally we used to get constant in every single other equation that we are about to make, but in this case this is the primary equation from which I'll have to build rest all other equation. Okay, for example, there is like Coulomb's law, which you will study, and then we will be like doing gravitational, I mean like universal law of gravitation. In those situation you will end up getting like g, and then in Coulomb's law you'll end up getting like k. So those are constant, which we will find out, actually using doing the experiment, such that all those parameters are taken to be like unity. Okay, in that situation I'll end up getting the constant, but this is the primitive equation. So from this equation we are going to build all other equation. Okay, so if I just put mass to be like 1 kg and then acceleration of that particle to be like 1 meter per second square. So that will be equal to 1 Newton. So that is how I'll have to build in this situation, because from this equation we will build rest all other equation. Okay. So this is actually the foundational equation. Therefore, I'll just take it straight away. The proportionality constant in this situation to be like 1. So here you are going to have K proportionality constant, which is equal to 1, right? Therefore, instead of writing it as F, which is proportional to m acceleration, we could actually put it straight away. That will be like vector F, which is equal to mass times the acceleration. Okay. So here also the force directly depends on the direction of the acceleration. Okay. So direction of the force depends on the direction of the acceleration, right? So this is the mathematical relation that I've got using the Newton's second law. So force is directly proportional to rate of change in momentum. So when you do the differentiation in Newtonian mechanics, mass is constant. Therefore, we ended up getting a vector F, which is equal to m times vector A, right? You shouldn't have any doubt in this thing. Let's see one application for this second law, right? Let's consider a situation where I'm going to catch the ball. Okay, so the final velocity of this ball is going to be 0, right? So let me take like two cases. In the first case, let me put it this way: the initial velocity was like 10 meter per second. Okay, so I'm just randomly choosing some numbers to it, right? So here the velocity was downwards, therefore it should be like negative 10 meter per second. Anyway, in this case I've just put the magnitude. Okay, so here I'm just going to catch the ball, which means the final velocity of that particular ball is going to be 0. So that's the situation. Fine. So we are just going to make like two cases for this particular scenario. So in the first case, the time taken by me, okay, while catching it, the time taken by me to bring the ball to rest was like 0.1 second. Okay, so in the first situation, I'll take the interval to be shorter. So the shortest interval that I'm going to choose is like some random number. Let us put it this way, which is equal to 0.1 second. So that was the first situation, right? So in the second case, same thing is going to happen. The thing is, the velocity of the ball was like 10 meter per second. So same with same initial downward velocity, it reached my hand and I caught the ball. So final velocity of that particular ball will be like 0 second. But in the second case, I just moved my hand a little bit backwards, which means I didn't bring the velocity of the ball to 0 instantly. Instead, I took like some extra time when compared to the first situation. Okay, so in the first situation, the interval was closer. So in that case, I just took that closer interval to be like 0.1 second. In the second situation, I just moved my hand little bit backwards, which means I just took some extra time to bring that ball to rest. Okay, so that extra time accounts to that longer time interval. I'm just going to take that longer time interval to be like 1 second. So that was my second situation. Okay, so let us see in both those situations how should be the impact of force on that ball. Okay, so the impact of force on the ball will also be felt in the hand. So that is what is the Newton's third law. Okay, as if now let's consider only the ball. Okay, so in the first situation, I just brought the ball to rest instantly and the time was so small that too the time was equal to 0.1 second. In the second case, same way I brought the ball to rest, but the thing is I just took some extra time, which means I just moved my hand little bit extra backwards. So that extra time also should also be accounted. Okay, so when I was moving my hand backwards, still the object was at some velocity. The velocity was decreasing at a longer interval. Okay, so that is what these two situations actually represent. So in those two situations, how was the impact of force on the ball? That's what I need to study. Okay, so from the second law, we actually know force is actually it is directly related to the acceleration, right? So it is directly proportional to the acceleration. So force should be equal to ma. Okay, so in both those cases, mass of the ball was same. Only thing that is going to differ is actually the acceleration. So from the acceleration, let me find out how far should I have to give extra force to stop that particular ball. Okay, obviously it is pretty obvious. In the first case, I should have given more force when compared to the second case, because in the first case I brought the ball to rest in a shorter time. Okay, which means I'll have to give more impact to the ball. Therefore, in the first situation, the force that I gave to the ball should be greater. Same way in the second case, the force that I should have given to the ball will be less when compared to the first, because in the second situation, the ball came to rest after some extra time, right? So force directly depends on the acceleration. So in this case, it is pretty obvious acceleration in the first case should be greater when compared to the second case, right? So let's find the acceleration in a numerical fashion and let's verify that the force in the first case is actually greater when compared to the second case. Okay, so in the first case, acceleration should be equal to final velocity minus the initial velocity divided by the time interval, right? So the final velocity here in both those situations was, in both those cases, was actually equal to 0. Therefore, acceleration A was equal to 0 minus the initial velocity. What will be my initial velocity? Initial velocity is 10 meter per second. That too, it is actually acting downwards. Therefore, you'll have 0 negative of negative 10 meter per second divided by the time interval. So the time interval here is like 0.1. Okay, so obviously if you do the math, you'll have like 10 in the numerator, minus and minus becomes plus, and then divided by 1 by 10, that's going to give me like 100 meter per second square. So that will be my acceleration, which is like 100 meter per second square, right? So let's consider it to be this way. Let's, in order for easy understanding, let's take the mass of this ball to be like 1 kg. So that is like extremely high, but the thing is, for easy understanding, I'll just take the mass of that particular ball to be like 1 kg. In that situation, force that was acted upon that particular ball was equal to 100 newton. So that should be the force that I need to give to bring that particular ball to rest in 0.1 second. So that's what that actually represent. Okay, so in first case, acceleration was equal to 100 meter per second square. Let's see what was the acceleration in the second case. In the second case, same way, you do the same thing again, which is like final minus initial divided by the time interval. So final was like 0, negative of negative 10, right? So final minus initial divided by the time interval. So time interval should be like 1 second. Okay, so if you do the math, it's just straight away, which is like 10 meter per second square. So obviously in the second case, the acceleration of the ball was lesser when compared to the acceleration in the first case. Okay, in the first case, I brought the ball immediately to rest. Then in that situation, I should have given more force to it. Okay, therefore the acceleration was greater. So in the first case, the force given by me to the ball was greater because the acceleration was greater. Because we know force is directly dependent on the acceleration. In the first situation, acceleration was 10 times greater when compared to that of the acceleration in the second situation. Okay, so force in the case of the second situation will be less when compared to the force that I have given in the first situation, right? So in both those situations, I just brought the ball to rest, but the thing is, the time that I took to bring that ball to rest was like different. Okay, so based on the time that I'm going to give to bring it to rest, I'm just going to give like extra forces depending on the situation. Okay, so this is the application of the second law that we have seen. So you should be clear with the applications that I've seen, that I've taught you over here, right? So force is directly proportional to the rate of change in momentum, which means how far I'm changing its velocity. Okay, if the mass was constant, then in that situation, how far I'm changing the velocity is directly dependent on the force that I'm giving on that particular object. Okay, so you shouldn't have any doubt in the second law, right? So let's see one more example to it, and then we'll jump into the third law. Okay, the other situation that we are going to consider is from uniform circular motion. From the last chapter that we have already learned, we know for a particular object to move in a circular path, I'll have to give centripetal acceleration at every instant. Okay, so whenever you have like acceleration, the velocity is obviously going to change. So in this situation, so it is going to change such that it's going to move in a circular path, right? So when you have acceleration into it, obviously if I put a mass in front of it, you will have like force into it. Okay, so here in this case, to get centripetal force FC, what I'll have to do is I'll have to multiply the mass times the centripetal acceleration. This is obvious, right? So when you have an acceleration to it, the force that I gave to that particular object was equal to the centripetal force, which is nothing but the mass times that particular acceleration. So that acceleration will be equal to m. Okay, so the modulus of that particular centripetal force should be equal to mv square divided by r. This is something that we have known. Centripetal acceleration is something that we have known. Only parameter that I introduced extra was like mass to get the force to it, right? So this is something that you might have felt. You just take a rope and then tie a stone at other end of the rope. Start swinging it. When you start swinging it in a circular motion, you will feel at every instant you are just pulling it inwards. The force that you need to give to pull it inwards so that the string is also attached and the object is moving in that particular path, right? The force should be equal to mv square by r. If that was the case, then it will move in a circular path. If the force was greater than mv square by r, then it will just choose a shorter path. Same way, if the force was lesser, then in that situation the string will break, and the object will start moving tangent at the particular point where the string break. Okay, so this is what you need to know regarding uniform circular motion and then the force that is needed. Okay, we will do many concepts that are related to the circular motion in the gravitation chapter. Okay, so gravitation chapter mainly comes around like earth moving around the sun, or else the satellite moving around the earth. Okay, in all those situations we will find the centripetal acceleration using those universal gravitational formula. Okay, so law of gravitation formula. As if now what you need to know is when an object is moving in a circular path, you need to have a centripetal acceleration to it. When you have centripetal acceleration, obviously you will have a centripetal force which is directed towards the center. This is something you might have felt while just swinging something in your hand. Okay, so this should be clear, you shouldn't have any doubt. Let's move on to the next final law, which is like Newton's third law. So this is the famous one, which is every action has an equal and opposite reaction. When you're going to push something forward, you'll have the same impact on you, right? Which means you'll be pushed backwards. So that is like the third law. In the last scenario where we did see was with related to the ball. Okay, so in that situation, in the first case, I just brought the ball to rest quickly. Therefore, the force was greater on the ball. Okay, which means I just gave more force to the ball. You'll have the same impact on your hand. Okay, so in the first situation, your hand is going to hurt you more when compared to the second case, because in the second case I pulled my hand a little bit backwards. Therefore, in the second situation, the force on the ball was less. So if that was the case, then the force that I gave to the ball was also less. Same way, the force that acted on my hand is also less. So in the second situation, so in the second case, and the hand is going to hurt a little bit less when compared to the first scenario where it will hurt more because I gave more force. So the impact will also be greater on my hand also, right? So that's the thing. Every action has an equal and an opposite reaction. So that what this statement actually represents. So if I'm going to generate an equation for this particular statement, it should actually be an vectorial representation, because in the situation one is acting forward and the other one is acting exactly opposite to it. So if that's the case, then I'll have to put a negative sign. That too, it should be related vectorially. Okay, so in the first situation, force on the first object due to second object, which will be like F12, that is equal to the negative of force on the second object due to the first one. Okay, so this is how the relation should be, right? Force on the first due to the second because of the second will be equal to force on the second object because of the first one. Those two things will be oppositely related. That's what this represents. Every action has an equal and opposite reaction. Okay, so I will be able to put negative sign on either of the equations. Okay, I could actually put it on the left hand side, or else I could put it on the right hand side. It doesn't matter, but the thing is, both those things are oppositely related, that too in a vectorial fashion, because force in and itself is actually a vector quantity. Okay, so now let's see the application that is directly related to the third law, which is nothing but the law of conservation of the momentum. Okay, so even though the statement actually represents law of conservation of momentum, this is not actually a law, because this is from the direct implication of the third law. Okay, let's see what that actually is. In the first situation, so there are like two conditions. One is like before collision and the other one is like the after collision. Okay, so in before collision case, I just took like two masses. One is like m1 and the other one is like m2. That is like before collision. So I'll just stick to certain notation u and then the v. Okay, just stick to the same notation, because from this chapter onwards you'll have like this initial velocity to be like u and the final velocity to be like v, and then you'll have like u1 v1 and all those things. Okay, I'll just use the same notation in upcoming chapter also. Therefore, just stick to the same notation that I'm about to use here. Okay, so here initially the mass was like m1 and the initial velocity of this mass was equal to the u1. Okay, so that's how it's going to be. So the initial velocity was also equal to u1. Same way, the next mass was like m2, the velocity of it was equal to u2. So this was before the collision. Okay, so when the collision happened, what actually happens is the first mass would have given certain impact to the second mass. Okay, so that will be the force given by the first mass on the second mass. Okay, which will be like force given on the first given by the first mass on the second. Okay, so force on the second mass due to the first one, which will be like F21, that will be equal to and opposite of that of the mass of the force that is experienced by the mass m1. Okay, so it will be like force on the first mass due to the second mass. So these two things will be oppositely related, because we know from the Newton's third law, these two are opposite to each other vectorially. Okay, so F12 will be equal to negative of F21. So here I didn't put the negative sign because I have just represented the direction straight away. Okay, so in this entire situation, I just took the motion to be like one dimension. Even if it was like three dimensional, still the same law of conservation of momentum is going to work out properly, because you just have those extra components into it, right? So this is big from the direct implication of the third law. Therefore nothing else is going to change. Only thing that will come extra is like I cap, j cap, and all those other things. In this situation, I do not want to worry about those vector things, because the entire motion is just the one dimensional thing. Even if it was like three dimensional thing, it will work out. Okay, so here whenever you in the question, if you see like collision, explosion, and all those things, okay, whatever happens when something is going to divide, split, or when something is going to collide, momentum conservation will just work out, because forces will always be equal and opposite to each other. Same way, the time interval that those two things are going to be in contact will be same for both those objects. Okay, we'll use that thing to get the momentum conservation. Anyway, what you need to know is whether it is like collision or explosion, you will be able to use momentum conservation. So we will see multiple sums while doing PYQs. As if now, what you need to know is you will be able to use momentum conservation in every situation. But the thing is, if it was like elastic collision, inelastic collision, you have multiple things into it. We'll do those things in the next chapter. So energy will not be balanced in every situation, but the thing is, momentum will be conserved in all those situations. Okay, fine, you should be clear. So now after collision, I'll just put some other notation, which is like after collision, those two velocities will get changed depending on the force that has been generated between those two masses. Okay, anyway, it is going to be equal and opposite to each other, so accordingly the velocity will change. Let's take the final velocity of the first mass to be like v1. Okay, same way the final velocity of the second mass will be like v2. So that is how I'm going to consider. Okay, so now what I will do is I'm just going to use the third law, which is like force on the first object due to second, F12 will be equal to negative of force on the second object due to the first object. Okay, so let me expand this equation. F will be equal to m times a. So instead of acceleration, I'll just put in final velocity minus initial velocity divided by the time interval. So with respect to the first one, F force on the first object due to the second one, so that will be like mass. So this m1. Okay, so it will obviously be like m1, and then what was its change in velocity, that gives me the acceleration, right? It should be like final velocity minus the initial velocity. So final velocity of the first object was equal to v1 vector v1 minus vector u1. So that will give me the force on the first object due to the second object, which is equal to negative of force on the second object due to the first object, which will be like m2. Okay, same way you'll have like final velocity, which is like vector v2 minus vector u2, right? So divided by the time interval. So time interval will be same for both those objects, right? It will have the same, the interval of time will be same with respect to both those masses. Okay, so how far was in contact will be same for both those masses, right? Therefore del T is going to be same for the first mass, same way it will be same for the second mass. So those two things, for those two things, I'll be able to divide it with del T. The time interval is going to be same for both those masses, therefore I'll just cancel it out. So del T, those two things will get cancelled out, right? Now let me do the inner multiplication, and I'll just rearrange it. Once I rearrange it, you'll get to know clearly that the initial momentum was equal to the final momentum, or final momentum was equal to the initial momentum, whatever it is. Okay, so now let me do the inner multiplication. So if I do the inner multiplication, you'll have m1 vector v1 minus of m1 vector u1, okay, which is equal to minus m2 vector v2 plus m2 vector u2. Okay, let me do the rearrangement thing. with respect to the initial momentum. So initially the velocity was equal to u1 and then u2. So let me put the initial momentums on the left hand side. So it will look something like this: m1. So it will be like m1 u1 will go to the right hand side. So you'll have like m2 u2 plus m1 u1. So let me write it on the left hand side. So you'll have m1 vector u1 plus m2 vector u2, which was equal to, if this goes to the left hand side, I'll write it on the right hand side. So you'll have like m1 vector v1 plus so m2 vector v2. So that's how it's going to be. Okay. So when you look at this formula, when you look at this relation, it is pretty obvious that the initial momentum, which was like m1 vector u1 plus m2 vector u2. Fine. So to make this equation simple, I just took the entire direction to be positive. Fine. So the initial velocity in both those situations was like positive. Same way, the final velocity was also positive. So that need not be the case in every single situation. In the first case, both those things, one could have been towards a positive and the other could have been towards the negative. If that was the case, then obviously you'll end up getting negative u2. Whatever the case is, this is the summation of vector addition of the initial momentum. Okay, just to make the process simple, what I did is I just took the entire term to be positive. If it was like negative, then those negatives then automatically pops up because I just used the vector representation, right? So m1 vector u1 plus m2 vector u2 gives me the final momentum, which is like m1 vector v1 plus m2 vector v2, right? After the collision, if the velocity of this one was like negative v2, then obviously in this case m2 negative v2 will just pop out. Okay, so we will do these kind of sums, okay, in the next chapter. In the next chapter, work, energy and power. So when you have like collision, one term will be like positive and the other one will obviously have negative direction into it. Anyway, as we are just doing the theory part, we just took everything to be like positive. If it was like negative depending on that particular situation, then automatically that negative sign will just come out. Okay, so the inference that you need to get from this law of conservation of momentum is, whatever the situation it is, always the initial momentum or initial momentum will always be equal to the final momentum. So it doesn't matter whether the energy is conserved or not, because in every single situation the force was generated by the first object and the second object. Same way, the second gave the force to the first thing. Okay, so in every single situation, the force was equal and opposite to each other. And same way, the duration of the force that acted on those two objects will also be same for both those two, for those two objects, because the time of contact is going to be same for those two objects, right? Only when the object is in contact, you will have like equal and opposite impact, right? So therefore, del T will be same for both those objects. Therefore, del T will get cancelled out to each other. The only parameter that will be left will be the momentum. So when you just rearrange it, we ended up getting the initial momentum, which was equal to the final momentum. Okay, so this law of conservation of momentum is actually not a law. Okay, so this is not something in law which we taken directly. The thing is, this is the implication of the third law that we have already seen, which is like every action has an equal and opposite reaction, right? So these are the things that you need to know regarding the three Newtonian laws. Okay, the first law is just a simple one, just the statement based one, which is like the object will be at rest or at uniform motion. Unless you give any external cause to it, it will be at rest or at uniform motion. So that was the first one. The second one was like force depends on the mass times acceleration. Okay, it depends on the rate of change of momentum. That's what we have seen with respect to the second law, and we were able to get an equation which is nothing but F equals ma, and we did see two application for that second law. Okay, we will see multiple things as if now for the logic we did see like two applications. Okay, same way the third law was like the simple super popular one, which is like every action has an equal and opposite reaction, which is like force on the second one due to the first one will be equal to the negative of force on the first one due to the second one. Okay, so the application that we saw for the third law was like law of conservation of momentum. Okay, so these are something that you need to know regarding the Newtonian laws, three laws. Okay, so next we will see the introductory part for the friction. Fine. Now we will see what is meant by friction. So friction generally comes into picture when you have two surfaces that are in contact to each other, right? So let's make it this way. You have an object that is placed on the surface, right? So in that situation, when you're going to push or pull the object, you will know that I need to use some extra force to pull or push it, right? So because there is some external agent that is restricting the motion of that particular object, that external agent is called as friction, right? So it will always act opposite to the direction of the pull that you are going to give, right? So we'll see those friction and all those things exhaustively in this chapter. From the lower grades, you should be clear with the concept of friction. Friction is something means it's just the external force that is acting opposite to the direction of the pull that I'm going to give, right? Okay. So we'll see all those types and categories into it. So first, there are like three categories, broad categories that we will divide the friction into, right? Okay. So the first thing is static friction. Static friction. So the name itself clearly suggests when both those objects are at rest. When the surface and the object that is placed on the surface, or it could be like two objects, whatever it is, when both those things are at rest relative to each other, okay, so they are traveling together with the same speed. In that situation, we will have static friction. Let me put this way. You have a table on a floor, right? If you want to push the table or pull the table, in the beginning situation, both were at rest with respect to each other. In that situation, if I need to push or pull, you will have an opposing force in it. That friction is called as static friction, right? So simple. The name itself clearly suggests what actually means by static friction, okay? So then comes the kinetic friction. So then you have the next thing, which is like kinetic friction, okay? So kinetic friction, same way, the name itself clearly suggests that the kinetic friction actually means when you have relative motion between the object and the surface or another object, you will have kinetic friction into it when both are in relative motion between each other, right? So when you are about to push the table initially, that time the friction that is acting on that table will be like static friction, which will be a little bit higher. Then once you start pushing it, it becomes easy for you to push it. So in that situation, you still have opposing force between those two surfaces, yet it is less when compared to the static friction. So that is called as kinetic friction, right? So both those things, static and kinetic, doesn't depend on the geometry and all those other stuff. The thing is, it doesn't matter what those two objects are, you will end up having static and kinetic friction. Initially, when you are about to push, when both those things were at rest, that is called as static frictions. Once the motion has begun, you will end up having kinetic friction, which will be a little bit lesser when compared to that of the static friction, okay? So these are the two main broad categories that you need to know. So there comes one special category which is called as rolling friction. So rolling friction comes because of the shape of that particular object, okay? So then comes the third one, which is like rolling friction. This is a kind of special category, okay? So when an object is in circular shape, it could be like disc or cylinder, whatever it is. When an object is in circular shape, you will have like very less friction that is acting on that particular object when compared to rest all other shapes, okay? So we will be able to categorize this one into two broad categories, which is like all those other geometrical shapes will come under the normal friction category, okay? So only thing exception is the rolling, which means the circular shaped object. So in those situation, you have rolling friction acting, okay? So why did I put it as a special category is because ideally, in ideal situation, in imaginary or ideal situation, that situation, the friction that is acting on a circular shaped object will be like zero, right? So we'll be doing those concepts in two chapters ahead, okay, in systems of particles and rotational motion. As if now what you need to know is we do not segregate friction based on the geometry or shape of the object, but the thing is only one special category is there, that is for the circular shaped object. Only in that circular shaped object, the friction that is acting will be comparatively less when compared to that of the other shaped object, okay? So rest all other shapes will be put into one single category, which is like friction, okay? So in that situation, you'll have like two things, static and then the kinetic friction. Only for circular shaped object, you get a special friction which is called as rolling friction, because in idealized situation, the friction that is acting on circular shaped object will be like zero, right? So we'll do those concepts in upcoming chapters. As if now you should be clear with these three categories of friction: static, kinetic, and then the rolling friction, okay? You shouldn't have any doubt in this part. So then comes little bit logic and intuition behind the friction, okay? So whenever you push or pull, there is this opposing force that is acting, which you could feel obviously, right? So if the surface was with a slippery surface, or if you pour some oil on a surface and you start dragging that object, it becomes easy, right? Same way, if you put a roller on that particular object, it becomes super easy to move it, because that is like rolling friction. That comes under special category, right? Okay, anyway, the point is It depends what are all the parameters does the friction actually depends is it depends on the nature of those surfaces, right? If it was like oil, it will be easy for us to push or pull. Same way, if it was like rough surface, it becomes harder, right? So all those many parameters together we'll call it as friction, right? So what all are the parameters that are responsible for the friction? That's what we are going to see now. So in this situation, you take an object and you place it on a surface, right? So the surface, when you look at the surface, it is pretty smooth, but when you look at a microscopic level, you will have ridges on those surface, right? This could be like two object, or it could be one could be like the earth surface or surface, and the other one will be like the object. Okay, so this surface, between those two surface, you will obviously have some ridges into it, right? Even in the above object and the below object, you will have those ridges. These ridges will lock on each other. Okay, so in that situation, you have like small locking between interlocking between those small ridges. Okay, so when you want to push that object, obviously you'll have to actually push against those ridges, right? So in that situation, you will end up having an opposing force generated between those two surface. That is called as friction, right? It doesn't matter the direction of the push or pull. The thing that it matters is once you start pushing it, obviously there will be interlocking between those two ridges, which will be responsible for the opposing force, right? You should be clear with this one. So friction will always act opposite to that of the direction of the force that I'm giving. Okay, so friction is acting opposite. So generally I will notate the friction with the small f. Okay, whenever I put like small f, it represents friction. Okay, you should be clear with that part. Then the force that I gave to that object was towards the right, so capital F will be towards the right, plus x-axis, right? So here in the first case, you had like microscopic ridges, right? Let me make it this way. I'm going to make it super fine, which means you do not have any ridges in that situation, right? So the best example will be like the crystalline material or two glass materials that I'm going to place on top of each other in that situation. So it will be like a perfect symmetrical shape to maximum degree. Okay, so in that situation, then obviously I should have like lesser amount of friction. But in the real time situation, when two surfaces are super smooth, in that situation the friction is actually dominating when compared to that of the scenario where you have like ridges. So why does the friction occurs when you have like two surfaces which are super smooth? Okay, so they are like perfectly smooth. The reason is because when you have two smooth surfaces, obviously there are atoms on both those surfaces, right? So these two atoms on two different surfaces will start interacting on an atomic level or on microscopic level. So in that situation, you have like a weak bond that is formed between those two surfaces, right? So when you have that weak bond formed, you obviously have to break that bond to push the surface, right? So in order to push those two materials, still you will have to give like extra force because friction is acting due to the intermolecular, partial intermolecular weak forces, right? Because of that one, you still have friction acting on those two smooth surfaces. So the conclusion that I'm going to give you is it doesn't matter how you choose the surface, it doesn't matter whatever material that you choose, depending on the material or the surface, you will still have friction that is acting. Some minimal amount of friction is going to act opposite to the direction of the force that you are about to give. Okay, so in the second case, where both those surfaces were smooth, you will still have friction because of weak intermolecular forces, right? I think you should be clear with all those stuff that we have discussed over here. Next, we will see an extra logic into it. Okay, so extra points into it, which is like necessary point that you need to know. Fine. So next thing that we are going to move is, I just told you it doesn't depend on the shape of that particular object, obviously. So whatever shape that you choose, you will most likely you will end up having the same amount of opposite friction. Okay, so in any specific engineering situation, you might have like different friction based on those small shapes, because the shape could be somewhat similar to the circular thing. In those situation, you might have like lesser friction acting on that particular object, right? So in overall thing, whatever the shape that you choose, you will have same opposing friction. Okay, so that's what I've written over here. So let me take like three masses. So in these three masses are of like same mass. Okay, so mass is going to be same. Only thing is, in the first situation I just had a different shape, and in the second situation I had like different shape. In the first one it was like rectangle, and in the second category I had like triangle. Okay, in both those situations, so the surface, everything was same. Surface is the same, the material is the same. Only thing that I've changed over here is like rectangle to triangle. Okay, mass is also same. In that situation, I'm going to pull it on the one side. In this case, it is towards the right. So the friction will obviously be acting opposite to that of that force, right? So friction will be acting something like this, right? So as mass, the material surface, all are same. Only exception that we will give is for the circular shaped object. In this situation, these two are some other geometric shape. Therefore, the friction that is opposing the force will be of same magnitude, so it doesn't actually depend on the shape of that object. Okay, whatever shape that you choose other than the circular thing, you will end up having the same opposite friction, right? You might have some small variations into it, but the thing is, when you learn this thing on a macroscopic level, or when you do more approximations into it, you will have like most likely the same opposing frictions to be acting on those two objects. Okay, which has different shapes, but still you end up having the same material. Okay, fine. So the friction, opposing friction is just the same thing. Same way, then obviously, even if you change the orientation of this particular object, right? So in this situation, it is like flat. In the second situation, it was like vertical. It obviously doesn't depend on the shape. Therefore, whatever the position that you place that particular object, you will still have the same opposing friction acting on that object, right? So the opposing friction is just going to be the same thing. That's what I've written over here. Friction does or doesn't depend. That's what I need to find. That's what I need to fill over here. So here it should obviously be friction doesn't depend on the orientation and shape of the object. Okay. So here friction doesn't depend on the shape or the orientation of the object. So shape actually means how we are going to change it. Fine. Orientation is how we are going to position it while dragging that particular object. Okay. Whatever it is, if the material and the surface are just the same, then you will end up having the same opposing force. So only exceptional shape is the circular shaped object. Okay. Rest all other things you can club it and put it into the same category. Fine. So now we will put numbers and start having new perception of friction and all those things, right? Okay. So here, as usual, you have like two surfaces. One is like the object, other one is the ground surface. Fine. In this case, I'm going to push the object towards the right with three different types of force. In the first case, it was like 2 Newton. In the second case, 4, and then the 6 Newtons. Okay. In all those cases, the object was the same, the surface was the same, right? So here you have like the maximum friction that could actually happen between these two surfaces was equal to like 5 Newton. So in the next class, we will do like how to find this maximum friction that is between those two surfaces. As if now, what you need to know is the maximum friction in this case was like 5 Newton. That's what we need to know, right? So I'm going to push this one to pull this one towards the right with a force of 2 Newton in the first case, right? Then obviously the maximum friction that could act between these two surfaces is like 2 Newton. It's like 5 Newton. Then in the first case, I'll be able to balance this 2 Newton. So the maximum force that could act as like 5 Newton, then obviously 2 Newton could be balanced. The force that I'm giving to push or pull this one is less compared to the friction that is acting between the surface, right? Therefore, in the first situation, the object will not move, it will be at rest. Got it? So the opposing force, frictional force in the first case was like 2 Newton. It couldn't be greater than 2 Newton. If it was like 3 Newton or 4 Newton, something like this, even the maximum opposing friction force was like 5 Newton. If it was like 3 Newton, then without any external reason, it will start moving towards the left, which is not possible, right? So I didn't even break interlock in the first case, right? The 2 Newton wasn't sufficient to break that interlock or the bonding that is between those two surfaces, right? Let me go it into the second case where I have given like 4 Newton towards the right. Then obviously, even in this situation, the 4 Newton will act opposing. So frictional force is good enough to balance. Therefore, in the first two situations, the object is not going to move, right? Because the maximum is like 5 Newton, then 4 and 2 Newtons could actually be balanced, right? Fine. So in the last situation, which means in the third situation, I was giving like 6 Newtons towards the right. The opposing force was like 5 Newton. That was the maximum limit which I could actually give. So with the leftover 1 Newton, it will start moving towards the right, right? So the frictional force in the third case will be like 5 Newton because the maximum peak friction has been reached. Therefore, I couldn't be able to go more than that of the 5 Newton friction. So this object will start moving towards the right with an force of 1 Newton, right? Because 6 minus 5, those two things will get cancelled out each other. With the force of 1 Newton, it will start moving. Once the object starts moving, you will have like kinetic friction coming into picture. Okay, so in that case the friction force will be less when compared to the maximum frictional force will be less when compared to this 5 Newton, right? So we'll do all those things in the next class. As if now what you need to know is frictional force is a kind of variable force. It acts opposite to that of the force that I'm going to give. So that too, it is like variable. If I didn't reach the maximum frictional force in that situation, the opposing force will be equal to that of the force that I've given to it. Okay, if the opposing force, if the force that I've given is greater than that of the F max, in that situation, the opposing force will stop by the F max, right? So with the leftover extra force, it will start moving in the particular direction that I pushed it, okay? Pushed it or pulled it, right? So you shouldn't have any doubt. The topics and theories that we have discussed, only one final part is left. With that, this session will get completed. Okay, so the thing that we are going to see finally is the normal reaction stuff. Okay, so this thing might not be related to friction, but this normal force is something that you need to know. From that normal force, we will be able to derive the formula for the friction F max. Okay, so this is like an extra concept which you need to know, so that we will be able to understand the frictional formula clearly, pretty more clearly. Fine. So here, so these are like simple balancing stuff. Okay, it will be like super easy. Let's see what actually it is. You have an object that is placed on the surface, and the downward force is only the gravitational force, right? Therefore the downward force is like mg. So what, this object is obviously not moving because the surface is good enough to balance this object. So obviously the net force on this object has to be zero, right? Only when the net force is zero, the object will be at rest or it will be at uniform motion. In this case, the object is rest, and then you still have gravitational pull because of the air, but the object isn't moving because this entire object is experiencing an upward force because from that surface. Okay, so it is pushing the surface downwards, but the surface is good enough to balance that object, which means the surface is giving an upward force. If the surface is not good enough or it is broken, then the object will obviously break down that surface and it will fall down, right? So in this case, the surface is strong enough to hold it. So if that was the case, then the mg that was acting downwards is balanced by the surface. Therefore you will have a normal reaction acting on that particular object, which will be like capital N, that is given by the surface on that object. Okay, so now if I do the equation balancing stuff, you will have summation of f of y, which is equal to 0, right? Because along the y direction the net force is going to be 0, therefore summation of force along the y direction will be like 0. So these are just the vector addition that I'm going to do. So mg was acting downwards, therefore you will have mg minus j cap, correct? And then you will have like one more component, normal reaction, which was acting upwards, plus n j cap, which was equal to 0. So in this situation, n will be equal to mg. If I do the rearrangement thing, here it was like unidirectional. Only thing is like j cap and j cap. Therefore, n should be equal to mg. So this is like pretty obvious. The normal force that was acting on that particular object was equal to mg, right? We didn't give any other external extra force. So this is like a simpler case where you have like normal force that is equal to that of the mg. In majority of the situation, the normal force will be like equal to that of the mg. Okay, so this is just a simple basic understanding. So with this normal force understanding, we will be able to build the concept of frictional force formulae and all those things. Okay, so the reason why I did teach you this as a separate thing is because you need to know normal force will not always be equal to mg. There will be situations where it is going to be something different. Okay, so that will be the second thing that we are going to see here. So here in this situation, this is just the same situation as that of the first one. Only thing that I've changed over here is you have a mass, same mass mg, which is like acting downwards. The surface is also the same thing. It is able to balance that object. The only thing that I'm going to give extra to it is the external extra force, which is like capital F. That too is getting added to that of the mg. Okay, in this second case. Okay, so obviously this normal force will be something different when compared to that of the first situation. Okay, so let's see how does it vary, whether it is increasing or it is decreasing. Okay, it is not going to be the same, right? Because obviously we are just giving an external force by pushing it or by pushing it, okay, with the hand, right? Okay, So in the second case, if I put like same thing, summation of f of y is going to be like 0 because along the y direction, this particular object is not going to move, right? So this is actually called as free body diagram, which means I'm just going to put vectors into it and I'm just going to solve all those things, right? If I do the force balance on in all those particular directions, I'll call it as free body diagram. We will do those free body diagrams in for different scenarios in the next session. As if now what you need to know is while doing these two things, there's this one parameter which comes always while doing this free body diagram, which is like normal reaction, right? So in the first case, normal reaction was equal to mg. In the second case also, while we do the sum of forces along the y, it was 0 because this object didn't move. So the normal reaction has to balance these two forces, right? So if you do add those things, you will end up having mg minus j cap that goes to negative direction, and then you will have like one more component which is like f minus j cap. You still have like one more component which is like plus n j cap, right? So when you add all those things, obviously the summation of force is going to be 0. That's going to be the left hand side, so that's 0. If you have any motion in this thing, then I'll put like m acceleration or something like that. In this case, summation of force along the left hand side and the summation of force on the right hand side should be the same thing. On the left hand side, you had all those different forces that was acting on that object. Summation of all those force in this case gives me the answer to be rest. Therefore right hand side was equal to 0. Okay, you should be clear with this simple mathematical stuff that we are doing. So if I do the rearrangement thing, I'll get the answer which is like n, that is equal to, if, if I move this one towards the right side, you'll have it becomes positive and then you'll have like mg plus f. Therefore, normal reaction that was acting on that object was equal to mg plus f. So in this case, the normal reaction was greater when compared to that of the previous case because I just gave extra downward push to it. So when I gave that extra downward push to it, the surface has to balance that one or else the surface will break, right? So it just gave extra upward force. So that extra upward force is nothing but the extra normal force that is acting on this object in this case, right? So you should be clear with the normal reaction that I'm just talking to you, right? Normal reaction shouldn't always be equal to that of the weight of that particular object. It could be greater or it could be lesser depending on the situation. We will do all those scenarios in the next session. As if now what you need to know is normal reaction will not always be same to that of the mass or weight of that particular object. It actually varies depending on the external force that is acting on that object, okay? These are something that you should know from this session. So in this session, we saw like 3 different Newtonian laws, okay? So those were like easy stuff. From the second and third law, we did see those mathematical relation. How should I figure it out, okay? Then we saw the application of the third law, which was like law of conservation of momentum. Then we saw brief introductory part for the friction, right? So in that introductory part, we did see like what category that I could make from the friction, which were like static, kinetic, and then rolling friction, right? We did see those things. Then how does it actually depends on the shape and the orientation of that object. It doesn't depend on the shape and orientation of the object. We did see that one. Then finally we saw like force maximum. If friction maximum was to certain number, then whatever force that I given, that could be the maximum limit up to which the opposing force could act actually on that particular object, right? So finally we saw like normal force. That's a kind of extra thing that we did see in this session, because from that normal force understanding we'll be able to generate the formula for f max, okay? So you should be clear with all those theories that we have discussed. You shouldn't have any doubt. With this, the video gets completed. Bye.